Okay, hello, hello. Welcome to the volumes and Bifrost lecture. Today we're going to be covering sort of how to make clouds, how to use Bifrost, which is Maya's procedural generation and programming language used to sort of like make volumes, simulations, particles, all that really cool stuff. So let's get started. First things first, what are volumes? Volumes are essentially a collection of voxels. And if you've ever used or like, if you ever played Minecraft, voxels are basically just 3D pixels. So think of them as like tiny, tiny cubes. Um, in 3D space, they are the smallest elements of a volume. So if you have ever like, drawn or used like Photoshop, that type of thing, a pixel is the smallest element of a 2D image and voxels are the smallest elements of a 3D volume. Yeah, so there's some amazing slides here. So you can see how like a voxel is sort of approximating the shape of the mesh. And in Maya, we've been using meshes with the triangle geometry. Voxels are just another way of sort of simulating that shape. And why use voxels then? If we've already used these triangles and these, extrusions and that type of thing, what's the point of using voxels and volumes? Well, volumes are a better way to sort of represent 3D objects, especially when you're working with simulations, as opposed to using a point cloud or a mesh, simply because they allow you to use depth. It allows you to sort of like have a 3D inside of the object. When you're working with meshes, there isn't really like an inside of the object. However, voxels, since it's basically just an accumulation of a bunch of tiny cubes, there is depth in it, and you can like manipulate each voxel individually. You sort of create really, really cool simulations and really cool effects based on that. Voxels also have a sort of resolution assigned to them. So the bigger the voxel, that means like the lower the resolution. So you can see here how like, if the voxels are really big, there's less of them, but they can't really approximate the shape of say this like this rabbit here or whatever this figure is here. But the more voxels or like the smaller the voxel size is, the better approximation you have of the shape. Now, also the smaller the voxel size is at the higher the resolution, which means there's a lot more of the voxels for your computer to be able to compute. So you really need to sort of find a middle ground as to like, oh, what resolution size I need, because if your resolution size is too slow or is too, if your resolution size is too low, then it will make your computer run a lot slower, which isn't good. So find a good middle ground between whether it looks good enough and whether, you can have enough detail. So in Bifrost, when you create a volume, there are two different sorts of types of volumes you can sort of create. And you can store the data, for both of them as well. However, these are the main two in which you can toggle between. The first one by default is fog density. So here, there's a really nice image here with points that basically approximate the density of the volume. So you can see how in the middle it's all red, which means it has a really, really high density. While at the very edge, the points are a lot smaller and also they're a different color, which means that the density is a lot smaller over the edges, which makes sense because if you think about sort of this cube here, there are less surrounding voxels at the voxels on the edges compared to the ones in the middle, right? Voxels in the middle are surrounded completely by other voxels, while the ones at the edge are only surrounded by voxels on one side, which means they have a lower density. Um, Alternatively, there's also the store level set option. Now, level set means that it stores data based on a signed distance field. Now, what is a signed distance field? Where are all these math terms? Well, a signed distance field is basically you take the voxel, the position of the voxel, and you find its distance to the closest distance to the edge of the geometry that you're working with. So if it's a negative value, this means that this voxel is inside of the mesh. And if it is positive, that means it's outside. So here in this image here, you can see how like the very corners of these voxels have a really, really high positive value because they're really far away from the surface of the mesh and they're outside, while they have a really high negative value if they're directly in the center. And it's represented here in this sort of like weird cube thing where black is a negative value and white is a positive value. And you can see how the white spheres get larger as it gets further away from the center of that mesh. So this is what a signed distance field is, and this is what the level set is used for. Now, you may also wonder, why even use scientists' fields? Well, scientists' fields are really useful, especially when you're working with certain geometries in which you want to sort of affect the inside and the outside. So, because the inside is negative and the outside is positive, you have a really, really easy way of sort of masking out the negatives, and sort of only getting positive values, which means you can do really cool things like this, where the sphere, when it intersects with this mushroom here, since it's negative on the inside, we can simply just get rid of all negative values and only operate on positive values. And therefore, we can sort of get this really cool intersection. And this is possible with signed distance fields simply because we have that distance, we have that polarity that we're able to use. Now, what is a field? Fields are very, very important when working with Bifrost and with working with clouds and simulations because they allow you to sort of define the behavior of whatever you're doing. Essentially, the definition of a field is a function that returns different values based on different positions. If you've ever used a matrix, they're very, very similar to that. The fields that you're working with are most likely going to be vector fields. If you ever like, taking calculus and that type of thing, um, it's sort of similar to like a slope field. Slope fields and vector fields is the same thing. Slope and vector, it's just called a vector because that's just the type of data that we're working with. But vector fields are a field that sort of store a vector, which is a direction and magnitude. For those of you without sort of like a mathy background, a vector field, you could just think of it as just a giant 3D space of arrows that point in various directions. So here you can see a vector field on this sphere that just points in a bunch of different directions. And on the right here, these are the flow lines. So you can see them sort of like curvy, which basically indicates the direction of travel. And they're very, very useful. And this isn't the whole vector field. This is only the vector field on the surface of a mesh. Reality is that vector fields are everywhere. So every single point in the entirety of the 3D space has a vector assigned to it. Um, and creating vector fields is usually really messy. So here, this image really limits it to the surface of a sphere. And you can see how the vectors point in a bunch of different directions, which you can imagine could be useful for sort of like moving these points around in sort of organic ways. So that leads me on to advection. Advection of a field is the process of moving a field based on another field based on time. So let's say I have a voxel field here. So it's a field of voxels, which basically approximates my geometry. And I also have a turbulence field, which is a vector field that sort of simulates turbulence, right? So remember in the previous slide, we have a bunch of these arrows pointing in different directions. Imagine each arrow as the direction of wind. This is what the turbulence field does, and it's basically just simulates real life wind. And if I advect the voxel field based on the turbulence field, based on a set number of time, I get an advected field. So I'm basically moving each individual voxel based on this field for a set amount of time, and that will basically transpose all the points. It'll move them around based on the turbulence field. And this can be very, very useful for creating natural phenomena, for creating like tornadoes, for creating clouds, water, that type of thing. You basically take a field of direction and you advect the existing field to sort of move every voxel, which is very, very cool. Now, what is Bifrost, right? So Bifrost is essentially Maya's visual programming language. You can create lots of very, very cool effects, so like procedural geometry, volumes, particles. You can even create like simulations, like water, arrow explosions, that type of thing. Very, very cool. And Bifrost has a lot of built-in effects that you can do. You just click a button and it creates like particles and things, but they don't allow you that much control over it. So we're going to be going over Bifrost's graph editor. Bifrost's graph editor is sort of, you see this graph here. It's a bunch of different nodes that connect to each other. Um, so you have these nodes, they connect to each other. It's basically like a visual programming language. You can also download a lot of these components off of the internet, which is really cool. There's a lot of like presets you can download here, or custom like nodes that you can make, and each node is basically just like a programming block. If you know Python, you can script your own nodes, which is very, very cool. But essentially, in the combination of all these nodes, you can create really, really cool effects, and basically use a bunch of math to sort of create the visual design that you want to achieve. You can also import and export volumes. So volumes are sort of stored within a VDB file, and different rendering engines have different ways of sort of rendering volumes. But you can download volumes from like online, that type of thing, and they can be animated as well. And these it's basically just a file format for volumes that you can share between a bunch of different softwares, for example, like Embergen, Houdini, using like Unreal Engine or Unity. VDBs are really great for, sort of downloading, exporting volumes, and that type of thing. Um, Volumes are also a bit special in that they are shaded slightly differently than you would normally do with a mesh. So remember how like meshes, we need to unwrap their UVs so we can actually shade them. So we're basically just modifying a 2D surface and applying that 2D surface and wrapping it around to sort of create the shading attributes. However, with volumes, since they're comprised of voxels, it's a bit different. You need to have a volume shader that a lot of rendering engines can support. So for Arnold, it's the AI standard volume. And the reason for this is because volumes are three-dimensional. They have an inside as well. So you shade each individual voxel and it can go through the object. If a voxel is, say, transparent, there are layers of transparency if you like add them on top of each other. And they don't use sort of this UV system that traditional shading uses. But essentially, a lot of the nodes tend to be very, very similar. But there are certain caveats that you need to think of. For example, the ramp node, right? The ramp node, if you've ever done sort of toon shading or if you've ever needed to sort of just get a range of colors, is very, very useful in traditional mesh shading. However, with volumes, it doesn't necessarily work. The reason for this is because, ramp is a 2D image, right? And you're trying to map a 2D image into a 3D voxel field. And that doesn't really work too well. So you need to sort of create an alternative. And the alternative would be to create a sort of 3D ramp. So ramping is like ramps along a 2D plane, but if there's a way to sort of create a 3D sphere of a ramp, then that's what you would do. And it's a great exercise, to sort of like think about how you would do that. A little hint you can do is using a phasing ratio to sort of get the direction of the camera input and sort of find the length of the ray that is casted from the camera to sort of create a spherical ramp. And you can find stuff online on how you can do this as well. Additionally, volumes can be shaded using a bunch of various data. So the way Bifrost works is basically it's just a manipulation of data. And volumes have a lot of data that is associated with them. For example, like the density mentioned earlier, or the sign distance, or the temperature of a volume, which is very, very useful, especially if you're creating something like fire or like a fire tornado, that type of thing. You can shade it depending on the temperature of the object and also like the density of the object. So maybe I want like really dense areas to be like red and really high temperature areas to be like orange, that type of thing. And volumes have very, very special properties that allow you to basically shade things based on those data sets. All right, so now we'll be going on to our demo. For this demo, you need to install the Bifrost Descend compound, which you can find at this link here. And the compound is basically just like a component or a node mentioned earlier. All right, here we have Maya opened. And the first thing you want to do with Maya opened is to sort of actually enable Bifrost. So you can go to Windows, Settings, Preferences, Plugin Manager, and over here, if you just search up Bifrost, you want to make sure that all these are loaded. So you have all of the Bifrost plugins enabled. And then once you have that, you should have access to Bifrost, which you can go over here. If you go to FX, if you see Bifrost here, then that means everything worked. Great. So first thing we're going to do is sort of give a visual representation of some of the stuff that we covered in lecture, or not in lecture, in the slides. So if we create a sphere here, what we can do is we can create a Bifrost graph. And in order to actually access the Bifrost window, you would go to Windows and you would go to, I believe it is the Bifrost graph editor. This should pull up the graph editor here. Now it's kind of useful for me to sort of like dock it off into the side here. So if I disable this lock, I can like sort of dock it off to the side. Um, or like down here and that type of thing. Very, very useful to sort of you don't have a bunch of windows lying around if you have the screen space for it. I already have a workspace, a custom workspace that I made for Bifrost, which looks like this. It's just basically putting this graph editor down here. And what you want to do is you want to select your sphere like this, and then you want to go and click Create Graph and you can see that nothing changed. And just because our input and our output aren't connected to each other. So this is Bifrost graph. You can sort of move around using the middle mouse button. You can use your left mouse button to sort of click on things, drag it around. Um, or you can use, like your like Alt middle click that also works if you're more used to like the panning from the viewports. Um, great. So this input is basically our mesh. You can see here on the right hand side here, there are parameters, and these parameters are each node has its own parameters, and this one takes in a mesh. So whatever is the mesh here is the mesh of the sphere. So if you see the name of the sphere is P sphere 1, right? And each object has a shape node that is attached to it. So P sphere shape 1. If I create like a cube like um, this cube is called P cube 1 that has a shape node that's attached to it. So what you want to do here with the input node is make sure the mesh is connected to um, the shape node of the object that you want. Like let's say I applied an effect to the sphere and I wanted to like move it to a different mesh, then I would basically just change the path here and that would work. So, but if you just like click an object and you create a graph from it, it's automatically in there. So if I just create this mesh and then I take it to its output, then you can see that basically nothing happened. But it's not like nothing happened. So when you create a Bifrost graph, there is the sphere and there's the Bifrost graph. And if I hide the sphere, then I'm just left with a graph here. And there's certainly nothing attached to the graph right now. It's just a single infinitely dense point because the input is not connected to the output. And if I connect the input to the output, you can see that the sphere comes out in. And the reason for this is because the input, right, I'm taking in a mesh as an input, and then I'm just putting it directly into the output, which is just the same thing as just the mesh existing on itself, right? So there's a sphere and there's also the Bifrost graph, but it's not very, very interesting right now. It's simply just, an input, output, and there's not much we can do with it. So what we could do is sort of show what we did in the slides of what, a voxel approximation of this would be. So I'm just going to turn off the grid here so it's not as distracting. And I'm going to go and click Tab to sort of bring up the search menu in which I can have a bunch of different nodes. And I want to go and do a mesh to volume. So if I type in mesh to volume, I can click enter and get this node here. And so I want to connect the mesh into the mesh and connect the volume into the output. And you can see this weird foggy sphere here. And this is basically the volume that we have created. Um, and you can actually visualize the voxels here by going to tab, going to a volume scope. And scope nodes are basically diagnostic nodes, which you can use to sort of view diagnostic information. So I could plug this into the volume and this geometry out, and it says it doesn't support it and turns red. And the reason for this is because the output expects a mesh, but I'm giving it a diagnostic geo, which isn't necessarily compatible. So if you ever have nodes that are red, this means it's not compatible, and you can view sort of down here what the error is. So in this case, the output node actually isn't a very, very good node to use as an output. Generally, you want to use a terminal node. So if I click tab and go to terminal, I get this node right here. And I'll explain what this does in a bit, but I want to take this diagnostic geo and turn it into this diagnostic field here. Um, so the way the terminal works is that I have three sort of inputs I can take. So final, proxy, and diagnostic. Final is what will appear in your renders. So anything that goes into final will appear in your render. Proxy is what appears in your viewport. And diagnostic is something that will appear in your viewport and it will not appear in your render. So it's just for diagnostic information. And there are these buttons down here that I can use to turn it on and off. So for example, if I just take this mesh and I put it into proxy, I can see the mesh again, right? I could turn it off, I can turn it back on, I could turn off the diagnostic info, I could turn it back on. Very, very useful if you need to test things and sort of just view things around. And you can always just, create more terminals too. Like this can go into here, like this. And maybe like I have a really, really big graph and this is all the way down here and there's a bunch of stuff up here. Well, I can just create a new terminal. I can turn that on and off, and which is very, very useful. So let me just go and delete this and plug this back into the diagnostic view. And you can see here how there's these spheres here, not these spheres, these cubes that sort of approximates the shape of this sphere, which is what a voxel is. Like each one of these cubes is not necessarily a one voxel, it's an approximation. So I think within each of these spheres, there's like four of actual voxels, just so it doesn't lag your computer as much. But you can see how it's approximating this sphere with this voxel here. And you can actually change the settings here. So there's a lot of different settings you can do with your mesh to volume node. For example, there's store fog density and the store level set, as mentioned earlier, as well as the resolution mode. And here's how you would actually change the resolution. So if I take my sphere and I scale it up, well then the Bifrost graph will scale alongside with it because it's taking the sphere as an input geometry, right? And you can see here with the resolution mode set to relative, the voxel sizes stay or they scale according to the size of the original object. However, if I were to change the resolution mode to absolute, they wouldn't necessarily do that. The voxels would be, an absolutely size based on world position. And changing the detail size changes sort of the size of the voxels. So generally, when you're working with things, you want to do a detail size of 0.1. Otherwise, you want to sort of like lower it to maybe 0.025, sort of to get a higher resolution for your final outputs. I'm just going to move this to 0.1 for now. And then I'll keep this in relative actually, because it's very useful for sort of testing things, so it's not as laggy because the voxel size will scale. Or you can keep on absolute if your computer is good enough like that. And you can see how in the volume scope, there is a lot of different properties that you can sort of visualize. And the one thing we're going to visualize is the tile tree. So this is the very first level of the voxels. If I increase this up to 2, you can see how there's higher voxels up here that are sort of larger in size. And if I increase this even more, this is Maya's way of approximating these voxels. And as the levels increase, the resolution lowers, which is very, very useful because it's an optimization method. You don't have to do anything for this. It's just here to visualize what voxels actually look like. Yeah, great. So I'm gonna go and disable this. And if I take this volume and plug this back into proxy and I disable this, then we just get this weird fluffy shape, which is, not necessarily the cloud that we want. So how do we actually create a real cloud? Well, first you want to do any sort of volumes, you want to convert your mesh into a volume. And then after that, you want to turn your volume into a voxel field. So you could just take a voxel field node, so you plug in your volume, take your voxel field, and you connect that out to your output, and it's not really working. And the reason is because this terminal expects a sort of either a volume or a mesh, and you're giving it a voxel field. So how would we actually, turn this voxel field back into a volume? Well, simple. You do a field to volume. So you take this voxel field, you plug it into this field here, volume out into the proxy, and whoa, um, what is happening here? Yeah, and the reason is because the interpolation is a bit different. So let me just turn this off into a level set here, and it's a lot better. Um, yeah, so when you turn it into a voxel field, there's a bunch of things that are different that changes here. So this voxel field is based on a signed distance, and previously it was set to fog density, which sort of screws things up. So you want to make sure things match here. Usually, working with the sign distance with the level set is generally a lot better for things. Yeah. So I'm gonna take the resolution mode to 0.1. Just keep that, not too high res. And then finally, in the sort of the field to volume, there's equally amounts of, the same amount of settings that you can sort of view. I can turn this over to sort of level set, and it sort of looks really wonky. Generally, when you do your field to volume, you want to keep that as a fog density. Um, so you want to do level set. So here, because you want to sort of use the data, the level set data that it provides you, in your sort of your calculations, and then when you finally turn that back into a volume for your render, then you can keep it as a fog density, just so it renders a lot better and it looks more like clouds. Great. And the detail size here, I mean, this is fine. I could turn this to absolute, which is a lot better. And I want to keep the detail size the same because here, this is based on absolute coordinates, and I want to use absolute coordinates here as well. Still, it doesn't really look like a cloud though. And what I can do here is actually, what are clouds? Clouds are sort of like a bit more squashed. So if I sort of squash this up, then the cloud is also a bit squashed as well. I'm just gonna go and move this back because I'll do something a bit later regarding the shape. Um, but clouds are sort of, they're not perfectly spherical, right? So what we could do here is actually use those fields that we mentioned in the slides. So what we want to do is we want to go and add back this field. So right now we have a voxel field and we want to move the voxel field based on another field. So we tug this voxel field into this field here and take the activated field out to the field to volume, nothing changes. And the reason for this is because we're not moving any of the voxels. We need to plug in a velocity field into the add vector field. So remember, add vectoring a field means taking in a field and moving it by a velocity field over some amount of time. So what we would do is we would just create a velocity field. So one of the really, really great velocity fields that you can do out there is called a fractal turbulence field. Now, fractal turbulence field is really nice for sort of getting those realistic wind movements. And so if I take this noise field and I plug it into this velocity field, you see how it sort of changed a bit. You can't really see the effect of this, but if I increase the magnitude here, so let's say like 5, we see how it moves. And the reason is because also like the time step is very low, so I'm only iterating it over like 0.1 seconds. So if I were to increase this up to like zero point 0.5, you can see how this changes the shape a lot, which is very, very cool. Very, very cool. Not really looking like a cloud though, so I'm gonna sort of bump this back down. I'm also gonna create a light so I can see things better. This. And the great thing about Bifrost is that it works really well with the viewport. If I turn on lights here, you can see the light starting to affect it. So maybe I want to increase intensity up. There we go. Looks more like a cloud. Looks a lot better. So for this sphere, I'm just gonna increase the size up a bit. I think that'd be good. Um, And then for the turbulence here, there's a lot of different settings with the turbulence. So the magnitude is basically how strong the turbulence field is. If I have a lower magnitude, it doesn't really move it that much. If I have a really high magnitude, it sort of moves it a lot. Um, I'm going to keep this around like 3. Maybe I'll increase the time step to like maybe 0.5. Um, and then for the fractal turbulence field, there's a lot of the other settings you can do. The number of frequencies sort of is like how much complexity there is. If I increase that, you can see how like it changes. So like one frequency basically just means like there's only um there's one wave that's controlling the turbulence field. If it increases up, you can see how it has a lot more complexity. So I think like this is a good value. You can also change the actual frequency of the value. So the higher you make this, the more like sporadic it tends to be. Um, you just want to achieve a sort of like a good um just sort of mess around with the values. Ratio is sort of like the complexity at the edges. Um, and I think like zero point 0.7 is generally a good value for these types of things. And there's frequency ratio, which is another setting you can do that sort of controls the ratio between the frequency and the actual ratio. So you can sort of get these cool relationships between them. Um, I think something like this is okay. This kind of looks like a cloud, but also kind of not really. Like it spits. It's mainly because I'm using a sphere as the base mesh that it doesn't really work. Um, but essentially, this is how you create clouds. But it's not very interesting. Right now we're only using one fractal turbulence field, and it doesn't really provide much complexity in the cloud itself. So what we could do is if we create a fractal noise field, and then we take the add node and we add the fractal turbulence field to the noise field, and we take that output as the velocity field instead. What this is basically doing is taking a fractal noise field, which is a scalar field. So a fractal turbulence field, this is a vector field, this is a scalar field. And I'm adding these two values together to sort of just change the strength of the turbulence field based on some arbitrary noise. And if I change the magnitude of this, you can see how the turbulence field gets affected. And what you can actually do is just visualize the scope of this. So just like how we could use a volume scope, we could use a field scope, um, a vector field scope. And what we could do is, since this output is a vector field, we can do this. We take this diagrammatic GML and we just create a new terminal. This can go in here. And whoa, what the hell is this, right? Well, this is actually the field. And fields are actually affecting this entire bounding box of the Bifrost graph, which is generally very messy. So what you can do with the scope is you can take in the input mesh, and you can use that as the bounds geometry. So it only works within the bounds of the mesh, and it's still really messy. So what you could do, if you maybe plug into probe geometry, where it's only the edges of it, um, and this is basically the field that we're advecting it by. So if I display the arrowheads, you can see them as arrows, or if I display flow lines, you can see them as sort of squiggly lines here, which could be a lot more helpful for sort of diagnosing what the field is doing. But let's say we increase the magnitude of this, right? You can see how the field itself is moving based on some noise. So it's not moving uniformly, it's moving based on this noise field here, as opposed to if I were to change the magnitude here, every single point on the field will move uniformly based on this magnitude. So um, if I have this fractal noise fields, it allows for a lot more complexity based on, I'm basically adding more complexity to this fractal turbulence field before I add vector. Um, and this field is basically, it's really great way to sort of visualize to get a sense of like how things are moving. Um, yeah, and I could just, turn this off if I don't want to see it. And maybe in the future I want to diagnose things. That's why it's nice to have a terminal here. And this is my final output terminal, but this is my diagnostic terminal. And I could just turn this on and off. Now, with this, let me just move this out of the way. Um, this affective field, generally with clouds, you want to use a turbulence field to sort of determine the general initial shape. But clouds have a lot more complexity around the edges as well. It's like layered complexity. And so what I would do is I would just add vector field again. So if I take another add vector field and I plug it into itself like this, and then I plug another velocity, turbulence field into here. So fractal turbulence field, I'll plug that into here. What I could do is, this is the main shape. I can have the time step be like 0.7. And then here I can have the time step be like 0.3. And then I can increase the frequency here, and increase the number of frequencies, increase the ratio. And this is a very noisy field. If I take this field here, I plug this into the scope and turn this back on. Right here, I'm having a lot more complexity in this, but since I'm advecting it by a smaller time step, it's not going to affect the geometry as much. And it's really good for sort of getting those extra details out there, sort of get around the edges, to make them a lot more cloud-like. Great. Now this is a bit messy, like, all these nodes flying everywhere. If I click the L button while selecting over some nodes, it will automatically sort of organize it together. So click L, it'll organize the nodes. Maybe I don't want to do that though, because, um, you don't really get control where it organizes things. A better way of organizing is, let's say, everything in the middle in here is sort of like creating the cloud fields, right? Sort of like giving it a lot more character and detail, while everything over here is sort of like the output. So what I could do is I could select these, or I can right click, create backdrop, and it creates a backdrop here. And what I could do is with this backdrop, sort of scale this up like this. And if I move this entire backdrop, it moves the entire thing. So it's very, very useful for that type of thing. And backdrops are really great for organization here. Great. So let's move that out of the way. Now, another thing we want to sort of do with this cloud is sort of assign a material to it. Right now, it's just the default cloud um, material here, but we want to assign like have more granular control. So what we could do is it's very, very simple. Just click tab, assign material. Wow, amazing. And we want to take this geometry in, and we don't want to give it a material because right now it has doesn't really have a material. And also, my bad, I meant to do this afterwards. So take this affected field into the field of volume, and then you want to assign a material to the volume. So you're not assigning a material to a field, you're assigning a material to a volume. And so what I could do is just click tab and I do AI like material. I can create materials here, or what I generally like to do a bit more is go into the Hypershade editor like this, and I'll just do an AI standard volume, and I will take this preset and I'll just go to default spiral arrow and replace it with the default Bifrost cloud preset. And what I want to do is middle click drag this into Bifrost. Then I can go and mess around with this. So this output volume goes into geometry, geometry goes out into the proxy, and we assign this Arnold material to it. And you can see out here in the attribute editor, all the different materials here. And you can always go back into Hypershade and sort of like mess around with this, sort of add all your Hypershade nodes in here, and it would affect the volume. Alternatively, you can also create the material in Bifrost to have a lot more control over it. So you can plug like fields into the material and change things up like that. But this is generally a simpler method if you're more used to working with Hypershade. Great. And if I render this, well, if I render this, you should be able to see something. And maybe it's because I don't have a light. All right, so I totally forgot that the reason it's not working is because this terminal only accepts a proxy. If I plug this into the final, now you should be able to see it in the render view. Um, so I guess you should probably always plug this into final and you can disable it whenever you want. Um, but since this is render view, it will only show up if you plug it into the final as a render view. Okay. Sorry for that little mishap there. Um, but I believe essentially you still have to go and turn this the ray depth up. If you don't have the ray depth, so let's say the volume ray depth is at 0, um, this just still works. It just the ray doesn't go through the volume. So you want to sort of increase the ray depth a bit, sort of give it more shape. Great. So this is how you sort of assign volumes to it, and you can sort of view the volume shader here a bit more. But scatter is the color of the actual shape. So this is the color in which the light, when the light hits it, what color it is. You can make it a nice red. You can change it up a bit. Just gonna keep it white for clouds. Great. Um, okay. Next, we're gonna go and sort of learn how to create a bit more complex advec fields here. So currently this advec field is kind of messy. It sort of like feeds into itself a lot, which isn't very good. Especially if you want to do this a lot more times. Like let's say I wanted to feed it into itself like 10 times. Then I would have to create like 10 different instances of it sort of feeding into itself, which isn't very good. So what I would do instead is I will firstly let me just delete this backdrop here. And the second advec field, I don't really need it. Um, so what you could do here is I'm just gonna go and take this advec field down a bit like this, like this. And then what I'm going to use is called an iterate node. Now, an iterate node, the way what it does is basically it takes in an input and then it uses the output back into itself a certain amount of iterations before sort of outputting it back out again. So what I want to do is I want to take this voxel field, put it into here, and then I can take this and sort of input it out to the field to volume. And it's going to error right now simply because the iterate node isn't connected. So if I just take this, copy with Control C, and I double click to go inside here, I get this right here. So if I take this voxel field out into this field and I sort of right click, set port state to voxel field, this basically is saying that this output port is a voxel field type. Otherwise, it wouldn't necessarily recognize the data that's going out. You want to make sure the types are the same. So I'm inputting a voxel field, I want to output a voxel field, especially because I want the output of this iterate function to go into the field to volume. And the field to volume accepts a field, which means the iterate must output a field. Great. So I'm just going to go and paste this back in. And what I'm going to do is I'm going to go take this voxel field, and I'm going to go plug this into the advec field, take the advec field out into the output. Whoa, what is this? The reason is because if I go into this input here, it has a max iterations and a current index. If I go back out, right now it has a max iterations of 10. If I turn this to 1, you simply just get what we had before. And what this is essentially doing is it's taking the voxel field, um, and it's putting it into the iterate function, right? And it's advecting it across this turbulence field that we did before. It's taking that advected field and it's going out into this output. And this output is going back into the input and doing this again 10 times. So you're basically applying this exact field 10 times, which is it's a lot of advection, which creates a really sparse and sort of weird cloud effect here. And essentially, we want to have more granular control over this. So what we want to do is use the current index, which is just a number between 0 and the max iteration. So like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is basically the index of like its iteration. And we want to use that to sort of make this less crazy as it goes on. If you remember, previously when we fed the advected field along itself, we increased the complexity, but we decrease the time step. And so what we could do is we could do something similar here, which might get a better effect if we take the index. So we take the index here, and if we want to convert it into a float, because the index is an integer, and we want to convert it into a float, which is basically a decimal value. And then if we multiply that with right-click create value, um, with like 0.1, we get this a much smaller value here, which is very useful for plugging into things like the time step and everything. So let's move this out of the way. And if I right click, I can do a scalar field. And so a scalar field is the same thing as a vector field, except it's a scalar instead of a vector. So instead of having like a bunch of arrows that point in different directions are all different sizes, it's just a field of the exact same number. So I want to take this index and I want to use the scalar field as a time for the fractal noise and the turbulence here. And what time does is basically it just sort of makes it evolve a bit more. It like moves the turbulence field along some time. So the turbulence field will sort of instead of being static, it will move it. So every time it iterates through the advection, it will sort of move the turbulence a bit and sort of change up a bit. But right now it's still really, really messy. And the reason for that is because for the advective field, every single time that we're advecting, um, it's advecting by a zero point 0.7, which is it's a really, really big number. So what we could do here is we can pull up the descend compound here. And what the descent compound does is basically it takes in these the index as a base, and it decreases the value over each iteration. Um, and we're gonna actually pull up the slides here. So the descend node is used in combination with the iterate node to sort of gradually decrease the number over its iterations based on some mathematical formula. So you can see here, this graph here is representing what the descend node will output after a certain number of iterations to the base value here. And the base value is basically just x in this f of x function. And you can see how this is useful for sort of creating different equations, for sort of decreasing the time step over time. And what we want to do here is for this first equation, we're just going to use an exponent of 0.5, 2.5, and 1, like this. So a exponent of 0.5, 2.5, 1, which is the default. And we want to go and basically take this output here, um, which is just an integer value, into the magnitude of these functions, type double, and the output of this is a, oh, why is this not working? No promotion exists from type double, type float. So let's just go and do a two floats like this. Um, take this float value into the magnitude. And I want to take this float value into um, this magnitude here, like this. And basically what this is doing is it's decreasing the magnitude as the iterations go by. So it sort of advects it less over time as the iterations keep going forward. And then we're going to go and take another descend node, this, and then we're going to go and take the index into the base, and we're going to use the second function here, which is here an exponent of 3, 1, and 1.3. So 3, 1, 1.3. And then you can use this as the time step of the advec field. Um, and once again, I need to go and convert it to a float, like this, into the time step. You can see now it looks a lot less crazy, a lot less crazy. What we do here, maybe I don't want this to be like so high. Maybe my I can probably decrease the number of frequencies here, or the frequency value here, since it's doing these iterations so much. So decrease the frequency, it's a lot less messy. Or maybe number of frequencies or ratio. That's not bad. And I think a lot of the issue is probably we're iterating it too much. So let's do the max iterations of like 5, or like maybe 2, 4. I think that's good. Let me sort of change it up a bit here. So for decreased number of frequencies to start with, and the magnitude is dependent on the time step. So something like that. I think maybe this is a bit too messy. Um, I don't think I want to go and plug in this descend node into the noise field. I think that sort of just messes with the magnitude a bit too much. We can sort of lower this value here, change up its frequency. That looks a lot better. You can go and mess around with it a lot, um, for different effects. Um, Essentially, this is how you sort of add more complexity. And it looks a bit messy, but you can go and create a lot of different. You can create the backdrop you want for different types of, or move it around. Yeah, great. Okay, but we still have this initial problem of like this is coming from the sphere, right? Like if we sort of squash the sphere, it becomes a lot more like a cloud shape. But since we're not squashing sphere, and since it's actually just like an actual sphere, it's a bit like round, and clouds aren't round. So what we want to do is actually sort of change the geometry of the sphere itself. So what we want to do is we want to do something called a point transform. So right here with this input mesh, we're just going to go and take a point, um, a transform point, I think it's called transform points. I want to take these points out, plug that into the mesh here. And nothing happens because we're not actually transforming the point right now. But instead of sort of manually changing the sphere here, we can do it in the graph, which allows a lot more flexibility in the future. So we can do an SRT to matrix, which stands for scale, rotation, translation to matrices. So you don't have to do any matrix math yourself. You could just like use this node instead. I'm going to plug that into the transform here. And right now it just disappears because the scale is 0, and everything else is 0. So let's turn the scale to 1, 1, 1, and we get our mesh back. But let's sort of like squash this a bit. So like maybe like 0.1 on the height here. It might be good to actually visualize um, what the mesh is looking like. So let me just bring out a terminal. Um, and this is what our mesh looks like. And maybe we could sort of just increase this up a bit. So maybe like 0.5, or 0.3, like this. And you can see how like sort of the bounds of these are like it's going like really, really far away from the mesh. And I think that's partially because of the way we're advecting it. It's going really, really far out. You can also change the bounds um, in the, I believe in the geometry. But what we're going to do here is we're going to go into the iterate node, and we're just going to go and decrease sort of the time step even more here. Um, so we take this out, it's really, really crazy. We plug this back in, it's less crazy. So let's just multiply this by a small value here. So say something like 0. Like 0.1 or 0.5, 3. Go. Now it's a lot less crazy. Um, and our cloud still looks pretty cloud-like. Okay. But the thing about clouds is that, clouds are sort of flatter on the bottom, and they're like, taller on the top, right? The bottom of the cloud is generally pretty flat. So what we could do is we can displace these points, and give it a bit more of a interesting like spawning location for the volume. So if we do displace points, we can take these points out here, um, and we can put this into here like this. I'm gonna take this displace points here, and it's like, wow, okay, the scale is a lot because it's scaling every single point out by 1. We turn it back down to 0. But what we essentially want to do is be able to sort of move these points based on some sort of noise. So let's just take a fractal noise field here, and we'll plug that into the weights. And it doesn't really do anything now, but if you increase the magnitude, number of frequencies, it should, and increase the scale here, um, should sort of move these points out. So the reason is if we set the scale to 0, it doesn't scale it based on this field at all. Let's scale to 1, it sort of moves it pretty irregularly. I think this looks kind of decent actually. But number of frequencies, we could probably increase that up a bit. Um, actually increase the frequency value, sort of give it a bit more of a wobbly look. Um, and the ratio, maybe a bit spiky. I think this is fine. Um, and this is really great for sort of like the base geo, but we're still not really getting the effect that we want with sort of a flat bottom and a sort of non-flat like top. And so what we want to do is first we want to get the point's position because we want to sort of move everything based on like the position of the point, right? If the point is on the bottom, we don't want to really move it. If it's on the top, we do. So what we want to do is we want to take, after we transform these points, um, delete this real quick. We take these points out into the output geometry here. And let's plug this into, because you can't. Let's take these, after we transform these points based on the scaling, let's go and get the position of the points. And then we just want to go and turn this vector to scalar. So the point position is a vector, and in order to manipulate each sort of individual like axes, we need to convert it into a scalar, which is an XYZ. And we want to go and take something called an array bounds, which gives us sort of a bounding box of um, the points here. And then we want to go and do a change range node, and we want to also connect that to the y value. Um, this. Um, yeah. We want to connect it into this y value here. I believe it's we want to do it like this. And the value goes in like this. So essentially, what this is doing is taking the bounds of the object, from the y position, and it's going to go and change the values here. So if I increase this up, you can't really see the results here. But essentially, if I take these points as um, into the displacement here as the weights, um, and see if I increase or decrease this, right, the value changes. And over here, if I increase the n value, this means that I want to increase the height of this, right? So it's not really affecting the bottom of it here, but it is affecting the top. All right, and you can see how it's billowing out at the top and it's sort of flat-ish on the bottom, but we're not really getting the sort of noise back here. And how do we sort of get this noise back? Essentially what we want to do is just add the noise back. But instead of using a noise field this time, we're just going to use a fractal noise. And the reason for this is because fractal noise is the geometry version of the field. And since we're working with point positions, we want to go and sort of change the geometry. Let me just plug this position into here, and I want this result to be the magnitude of it. Now plug this noise out into the weights. We can see how it's sort of flat on the bottom, and we're getting this noisy effect on the top here. And by changing this noise value here, we can sort of like get a more smoother result, or if we increase the frequency a bit more. And since we're converting it into a volume either way at the end, these spikes in self-intersecting sections don't really matter. Um, and we can change the range here if we want to sort of go higher, um, or just increase the number of frequencies. I think something like this looks pretty all right. Or you increase the ratio, it sort of increases how high up it goes at the edges, while the frequency is more like the entire thing. This is pretty decent here. And if I sort of disable this, the rendering of this, now this looks a lot more like a cloud. And you can sort of tweak the values here to sort of get a better um, ratio here. So something like this maybe. Um, I think that looks good. I think this looks good. Um, Great, and you have this sort of cloud here, or maybe it's a bit too spiky at the top. Sort of lower that down. But yeah, so this is necessarily how you would change the displacement of the actual points to sort of change the geometry up a bit to give the clouds a bit more of an interesting geometry to work with. And if we render this, it doesn't look half bad. Does not look half bad. Great. So, but this is just one cloud, right? Like, what do we want to do to actually like have a lot of different clouds? Like, what you could do is you could just take this Bifrost graph, not the mesh. You could just move the graph itself around. For example, if you take this mesh actually, and you were to sort of move it really far away, the Bifrost graph sort of disappears. That's because the graph itself has a bounds within this grid, and if you take the sphere out of the grid, it disappears. Instead, what you want to do is you want to move the graph itself out and scale it out like this. And you can see like right now, like it's hella voxely. As that's simply just because the resolution isn't that good right now. And this the actual sphere isn't that big. If I increase the size of the sphere, and I height this, it gets a lot more laggy. But you can see how like it's sort of since we're using absolute scaling, the voxels sort of fill that up a bit more, which probably isn't what we want and is lagging my computer. So let's turn that back down. Great. Okay. Yeah, so what if we want to do a C clause, right? You could just duplicate the graph and duplicate over and over again. But that gets a bit like, that gets a bit annoying. So what we want to do is sort of scatter the points. Sort of you want to take using Bifrost to create different instances of these. So let me create a plane. This plane will act as sort of me just like it's the plane in which we scatter these clouds over. Yeah, okay. So after creating this plane, what we're going to do is sort of use this plane as a sort of base to scatter these clouds. And so what we want to do here is that this input mesh is sort of like our transform and all that. I'm just going to go and I'm going to create a compound for organization purposes. And we just call this displace points, um, or displace cloud points. Um, and I'm just gonna take all of this right here. Um, and I can delete this terminal. I don't need that anymore. Take all of this, go copy, go inside of here, paste this into here. We take the input into here and the output like this. Um, and then go out here. We take this input here, and we take this output to this output here. So this. And then we can get rid of all this stuff in the middle. This. So just for organization purposes, what we essentially did is we created a new component that does what we just did. Um, just so I don't have a bunch of sort of nodes flying around everywhere. And so let's all click L, and it's a lot cleaner. Great. Okay, so how do we actually go and sort of scatter these points out? So what we sort of want to do is we want to go and first things first, we want to bring the plane into this graph. Um, so if we sort of copy this, duplicate, I believe this is an input node actually. Yeah, an input node. We can just change the mesh here. So the mesh here is p plane 1, and it would be p plane shape 1 for the mesh, I believe. Um, yeah, p plane shape 1 is the shape node here. Now we have access to the input mesh and also the plane, and we'll just call this plane, and then we'll call this cloud geo here, just for organization purposes. And then after we do that, we sort of want to scatter this geometry around. Um, so I'm going to go and create a new compound, and we'll just call this scatter geo. This is going to go and take in this plane, and it's also going to go and take in, right before we start moving everything, um, these cloud points. So after we disable out the cloud points, we're going to go and take this out like this. Um, yeah, And then this is our scatter geo. And then we go inside like this. And right here, we have our plane. And we should have, we don't have our output geo. And that's because you don't want to take the points in there. You want to take the cloud geo in like this. Bad naming here. Rename ports. So let's just call this cloud geo. And we can rename this port to plane. Take this mesh into this cloud geo here. And then we can go inside here. Yeah, and so what we want to do is just take this plane and take this output geo, and we want to sort of scatter the geo onto the plane. So the first thing we're going to do is we're going to go and take a scatter points. And this should allow us to go and take our input geometry, which is the plane. And then we want to go and sort of randomize the points so that we're scattering onto it. I can't type randomize point scale. This. So we put this into here. And then we want to take this. And we want to randomize the rotation as well. So we want all the clouds to rotate into different. We want to rotate all the clouds into like different positions so they're not all facing the same direction. I want to go and create an instance. Create instances. So I basically have all these points that are scattered around. Um, and then I want to go and create an instance of the cloud geometry at every one of those points. So if I take the points in here, take the cloud geometry into the instance geometries, and then I take these instances and I bake them, bake the instance geometries. Sort of this basically just means I'm taking all these instances and turning them into actual meshes. Because previously they're instances, right? So this is an output of an instance, and I'm going to turn this into actual geometry that I can work with. And then I can go and sort of displace all these points. So I take an output node like this. I can take these merge meshes and I can go and sort of plug this into our displacement. So if I take this, go out here like this, I'm gonna take this displace cal points and I sort of just plug this back in like this. I can take the meshes in here, and then go out like this, into the outputs. Yep. And this is going into our transform points, and it's also going into our sort of our point positions and that type of thing. Yeah, and that should be able to give out our displacement output here. This goes into this, and this outputs in scatter geo. So if I take these points out here and turn them into a volume, and lag, we can see how I sort of basically just took all of these clouds, I randomized the points, and I spread them out across this plane. Um, and if we go inside here, like this, focus, um, we can sort of just mess with the randomization amounts here. So right now there's 1,000 points, which is quite a lot. If I lower this amount, a lot better. Um, Lagging right now. Let me do like 100 points. And you can see the density of this just gradually lower. Um, you can also scatter it based on some sort of noise or some sort of density value. Let's do 5 points, maybe 10 points like this. We can do a bit more, 50 points, uh, 30 points. Oh, that doesn't look that bad. And you can see here, it looks pretty good. And yeah, this is how you sort of scatter the points. And we can create a sea of clouds like this. We can randomize the scale by like making something really big. Like let's say this is 5. So it's random between 0.5 and 5. Maybe that doesn't look too good. I think the default actually looks pretty decent. Change the rotation as well, based on the random points. But essentially, this is our sea of clouds. And it doesn't look half bad actually. So if we render this, You can see our sea of clouds. Nice. You can also see how like at the edges here, you can see it sort of like cutting off like that. And that is because, again, with our bounds of the graph itself, the graph needs to be bound to a like a larger location. And this is just it's too small for it. And scaling this up doesn't really help. What you could do is, I believe you can just sort of scale the plane down so it fits within those bounds. Plane is currently a bit too big. Um, so if the plane is scaled down to sort of fit within those bounds, you won't have those weird cutoff issues. Um, and then you can just sort of just move this graph up to the sky, increase the size up a bit, and now you have your sea of clouds. They're kind of right now all at the same level. So what we could do is sort of increase the displace the y values as well. Um, and you could do that into the scatter geo here. Um, and you can just displace the points again. After you sort of bake instances of geometry, you can sort of convert these back into points. You can move them around based on some noise. Um, you can do that to begin with over here as well. It doesn't really matter what step you do it, you can achieve different effects based on that. So yeah, essentially this is it. This is the tutorial. And yeah, this is the Bifrost clouds. Nice.